So projectile motion can have air resistance, most commonly does, and the two cases we look at are if the air resistance is proportional to the velocity or to the square of the velocity. And in this question, we have the situation where the air resistance is just straight proportional to the velocity. So a projectile is fired with velocity vector v equals 15I plus 30j. Air resistance is proportional to the velocity with constant of proportionality 1/5, right? So proportional to the velocity with constant of proportionality 1/5. Find the Cartesian equation of the motion. So we might find parametric first with the horizontal and the vertical, maybe in terms of time, and then eliminate the time parameter to put them together to find an equation with y and x together. That would be a great idea because then we could plot that maybe on a program like Desmos and see what the projectile motion looks like as distinct from possibly the classic inverted parabola. It might have a bit of a push across type of skew. So here's our velocity vector, 15I plus 30j. We've got to take, gravity is 10, and we've been told that it's proportional to the velocity and the constant of proportionality is 1/5. So basically, it'll be, you've got minus 1/5 of V is your drag there, your wind resistance. All right, so I think we will consider this both horizontally and vertically, and then get equations of time for each of those, horizontal and vertical displacement in the end in terms of time, and then pop them together to eliminate the time and get your Cartesian equation. So the first thing I'd like to do is start with horizontally. Horizontally, we've got our overall horizontal force is equal to, now there's no gravity acting on it, so it's simply the air resistance is acting upon this horizontally and in the opposite to the direction of motion. So it's minus kv, now the horizontal velocity, which I'll call Vx, and that's times m, of course. So minus m kvx, and that would be all. So that's the forces equation there. I can divide out the mass to get the acceleration horizontally is equal to minus k, the velocity horizontally, which is often referred to as x dot. Now, this is a classic differential equation which we should know the answer to straight off the top of our heads. I'm going to run through that now in a classic way, then come back and we'll put the answer through for you. But classically, you might be given that dy dx is equal to minus ky, and asked to solve that differential equation. So you've got dy on y equals minus k dx. And so you've got the natural log of y is equal to minus k x plus c. Now, there's got to be a discussion about that absolute value signs around the y, but in terms of our horizontal velocity, we're always going across in what we're going to declare to be the positive direction, and then the whole process will end. So we're not going to get a negative velocity there. So this is not going to be a problem for us, and we're able to get rid of those. Now, this means that e to the minus kx plus c is equal to y. And that means that a e to the minus kx equals y, where a is equal to e to the c. Because if you have, I'm using that rule that says if you have a to the m plus n, that's equal to a to the m times a to the n. And I'm turning it back into there. So that's our classic answer to that. If we have this situation, then we could straight say y is a e to the minus kx if we took care about those absolute values in the midst of the integration. But otherwise, without any difficulty, we should know that that's where that goes to. Now, this is the same thing because this is the velocity and this is the derivative of the velocity. So if you like, this is our y, and then this would be dy dx, wouldn't it? Because this is the derivative of that, the double dot, and that's a single dot. So it's exactly set up in the same way. So we could, without having to do a whole bunch of differential integrating, go straight to the fact that our x dot, because that's equivalent to our y here, is equal to a e to the minus k, and it's times by t. So we could go straight to that point. Because this is equivalent to our dy dx, but this is actually dx dot dt, isn't it? So dx dot dt is equivalent to dy dx in this over here. So that's where I get my t from. Okay, so I could go straight to there if I wanted to. Now, I'll just remove this. Now, I should have put in my constant of proportionality right at the beginning, which is 1/5. So let's just pop in a fifth there, and therefore pop in 1/5 right in there. And instead of writing it that way, how about we write that as minus t on 5 instead of minus 1/5 t. Get rid of this now, get rid of this, get rid of this. And there we are. We'd just like to find out what A is, and we need to just put in the values that we know. So at time 0, what is the vertical velocity? Vertical. We're doing horizontal. At time 0, what is the horizontal velocity? Well, horizontal is the I direction, vertical is the J direction. So at time 0, it's 15. See, the projectile was fired with that. So at the beginning, it's 15. So when t equals 0, x dot equals 15. So 15 equals a e to the 0. Now e to the 0 is 1. So a is 15. So I can pop that in here. And I have my equation for the horizontal velocity in terms of time. Now, I wanted to get the horizontal displacement in terms of time and the vertical displacement in terms of time, so I could then eliminate the time parameter and put those two together to make the Cartesian equation. So we need to integrate again to get to the next step. So I want to integrate this. Like this says dx dt is equal to 15e to the minus t on 5. So dx is equal to 15e to the minus t on 5 dt. So I'm going to do those two integrals there. This is x equals, just checking that you can see that on the bottom of the board. Yep, x is equal to, and you always get the same e stuff, so I'll put that down there. But in order to get that, I'm going to have a minus 75 there. So a fifth of 75 is 15. And plus c. All right, so my question would be, where is the projectile located at time equals 0? And we're assuming for our coordinate system it starts at 0, both horizontally and vertically. We'll mark that as our origin where it starts from. So when t is 0, x is equal to 0. When t equals 0, x equals 0. So I'm going to pop that in here. 0 is equal to minus 75 e to the 0 plus c. Well, e to the 0 is 1, so c equals 75. So I can pop that in back down here. I can say that x is equal to minus 75 e to the minus t on 5 plus 75. Now, it would be a good idea to just factorise that while we've got it. So x is 75 into 1 minus e to the minus t on 5. So I'll just write that down here to be able to keep that. X equals 75, 1 minus e to the minus t on 5. Now later on I'm going to want to know what t is. It may be easy to write x in terms of t from this, or I can't imagine it will be any easier from the vertical equation because that's going to involve another force. So I might, while I've got this here, write what t is in terms of x so I can do my replacement later on. So this is saying x on 75 equals 1 minus e to the minus t on 5. So x on 75 minus 1 equals minus e to the minus t on 5. Now if I put that together, I get x minus 75 on 75 equals minus e to the minus t on 5. And if I change, so it's not negative, both sides divided by negative 1, I get 75 minus x on 75 equals e to the minus t on 5. And if I flip both sides, 75 on 75 minus x is equal to e to the t on 5. So I just took the inverse to get rid of that minus. Now I can easily see what t would be. Take the log of both sides. Natural log of 75 on 75 minus x is equal to t on 5. So t is equal to 5, the natural log of 75 on 75 minus x. So I'll be able to use that in some way later on. I'll just erase this and pop that there for use later on. That from that I get that t is equal to 5 natural log of 75 on 75 minus x. So there's some good work done there vertically. I've got my acceleration vertically, I've got my velocity vertically, I've got my displacement vertically, and I've also got this parameter t in terms of x there nicely so that I can replace that when I get my vertical equation. So now we need to work vertically. And we'll just grab another pen here. And we need to now go and work vertically. So, what's happening vertically? Well, the mass times the acceleration vertically. Now there's two things happening. We've got gravity pulling it down, so minus mg, and we've also got this wind resistance, air resistance, pulling it down, so minus mk, and the vertical velocity, which I'll call Vy at the moment. That's y dot. Divide by n, and I get y double dot equals minus g minus k Vy. And now k is 1/5, the constant of proportionality, and Vy, the vertical velocity, is y with a dot on it. So here is my acceleration vertically all sorted out, and now I go through that same process of integration. Now, g is 10, so I can pop 10 in there, and I may be better off factorising that so that when I go to integrate it, it's easier. So that's actually minus 1/5 into 50 plus y dot, isn't it? When I factorise that minus 10 minus 1/5 y dot. So I'll just change that, put that in that format there. It's minus 1/5 50 plus y dot. All right. There we go. Let's do some integration. So this is saying that it's like we've got dy dx is equal to minus 1/5 50 plus y. It's the equivalent of that from, a more simplistic version when you're doing differential equations in extension 1, because this is the derivative of the velocity, and there's the velocity. So that's the type of thing I'm trying to solve as a standard equation. So I'm going to do this and then come back and show what this one means in that sense. So this is dy on 50 plus y equals minus 1/5 dx. So this is, if we do the integral of both of them, this will be the natural log 50 plus y in absolute values equals minus 1/5. Now that'll be minus 1/5 of x plus c. So that's how you would go ahead and integrate that normally. But I've replaced things so I can see what's going on, right? Y is actually y dot here, right? We've been asked to do dy dot dt because this is the derivative of the velocity of y dot with respect to time. And this is y dot here, right? So when I get to the end of here, this is 50 plus y dot, and this here is a t. So I end up with this equation here. Now, I can figure out what the value of c is, and I also have to worry about these absolute value signs as well. So let's figure out the value of c now, and then let's talk about the absolute value signs. When t is 0, What's the vertical velocity? 30. So I can pop that in there. When t equals 0, y dot equals 30. So I can pop that in there. Natural log 50 plus 30 equals 0 plus c. So c is the natural log of 80. It doesn't need absolute values because 80 is positive. All right, so I now know what our equation is. Our equation is the natural log of 50 plus y dot equals minus t on 5 plus natural log of 80. All right, now what am I going to do about these absolute values? Because when the projectile is shot up, that's fine. The velocity is always positive, which means the velocity is positive and a positive plus 50, that's fine. But when it comes back down again, the velocity starts to, it's negative when it's coming like vertically. So how do I know it's not going to overcome this 50 and maybe negative 60 and become a negative 10? So what am I going to do about that to be sure that I can remove those absolute value signs? Well, what I'm going to do is, given that I know that the velocity is positive all the way up to the top, when I do this calculation I'm about to do, I can assume that I don't need the absolute values, because at the moment, I'm going to worry about just the first part of the flight up till it comes to rest. So let me write down what that equation would be. If I assume the velocity is positive, which it is in the first part of the flight up till it comes to rest, then this would be natural log of 50 plus y minus natural log of 80 equals minus t on 5. So it would be natural log of 80 minus natural log of 50 plus y dot equals t on 5. So it's natural log of 80 on 50 plus y dot equals t on 5. So t equals 5, the natural log of 80 on 50 plus y dot. So assuming that I'm allowed to just not have them as absolute values, but just take the positive, I can come out that t is 5 times the natural log of 80 on 50 plus y dot, the vertical velocity. Now that's going to be the case for the first half of the journey, which means I can find basically the time of flight. Now, I'm just making a bit of an intuitive assumption here, like with a parabolic flight, if you get halfway there, then it's going to be the same time for the other half of the flight. So let's just see if it's going to give us a value that's going to let us assume that the whole time we can not worry about those absolute value signs. Well, when the projectile comes to rest at the top of its flight, the vertical velocity is 0. So I can find what time that is by putting the vertical velocity of 0, putting a 0 in there for y dot. And that'll give me 5 natural log of 80 on 50. 5 times the natural log of 8 on 5. So 5 natural log of 8 on 5. Whoops. And I'll get 2.35. Okay? I get that the time roughly to the middle of the flight. Now, I know that it's a bit skewed, but the time roughly to get there is 2.35 seconds. So that means the time for the whole flight, roughly, double that, 4.7 seconds, let's say. The time for the whole flight's 4.7 seconds. Now, once it's come to rest up the top, all right, the biggest the vertical velocity can get, like imagine it's just dropping straight down with no resistance, the biggest it can get is AT, right? The acceleration times the time. Now, the acceleration is 10, so in order to get a velocity, which is going to be a problem for us, right, a negative velocity of 50, if it's 10t, like AT, because it's at rest and v equals u plus AT, just dropping, then it would have to go for 5 seconds. Right? I'll just write what I mean here. Just standardly, v equals u plus AT, if it's going from rest at the top of its flight and dropping, then it's 0. Gravity is 10. And if we want the velocity to be 50, then t would have to be 5. It would have to travel for 5 seconds before we got a problem, before that got to be 50 in the wrong direction, right? And we're estimating that it only travels for 4.7 seconds. So I'm thinking it's a fair call here to go, don't worry about those absolute value signs. Don't worry about the absolute value signs in our equation. So if that's the case, we now need to work out what's y dot, if we can just not worry about the absolute value signs. So how are you going to work out what is y dot? Well, you can go through the same process as we did before. We get the natural log of 50 plus y dot on 80 equals minus t 5. We get e to the minus t on 5 equals 50 plus y dot on 80. So we get 50 plus y dot equals 80 e to the minus t on 5. So y dot equals 80 e to the minus t on 5 minus 50. So I'll write that down up here for my y dot. Y dot equals 80 e to the minus t on 5. Try to get a pen that will work. Minus 50. 80 e to the minus t on 5 minus 50. That's my y dot. 80 e to the minus t on 5 minus 50. And now I need to go up one more step to find my displacement in the horizontal. So I need y, right? So I'm told that dy dt, that's y dot, is equal to 80 e to the minus t on 5 minus 50. So dy is equal to that side dt. So y, if I integrate, then y is equal to minus 400 e to the minus t on 5 minus 50 t plus c. Now, we took it so that it starts from the origin. So when t is 0, our y is 0. So when t equals 0, y equals 0. So we're now going to place that in there. 0 equals, actually I've got to be careful, I need that equation. I'll do it over here. 0 equals minus 400 e to the 0 minus 50 times 0, which is 0 plus c. And e to the 0 is 1, so c equals 400. So I'll pop that in there. And I'm going to write it like y equals minus 400 into 1 minus e to the minus t on 5, and then minus 50t. just because 1 minus e to the minus t on 5 is something up here. So let me just write that equation down here. Y equals 400 1 minus e to the minus t on 5 minus 50 t. There's my vertical displacement. Now I can find my Cartesian equation of the motion, like the question asked, by putting, wherever it's got a t, put a version of x in there. Now, this is quite fortunate that we've done this way, because I can see that the bracketed 1 minus e to the minus t on 5 is x on 75. I can see that this 1 minus e to the minus t on 5 equals x on 75 from that equation. So if I see 1 minus t e to the minus t on 5, I can put x on 75. So y equals 400 x on 75 minus 50 times t. Now normally I'd have to replace the t. Now here I worked out before that t is 5 natural log of 75 on 75 minus x. So times 5 natural log of 75 on 75 minus x. So, I mean, that could be tidied up a little bit and you'd have your Cartesian equation. Y equals 16 times 75. Yep, 16x on 3 minus 250 natural log 75 on 75 minus x. That will be the equation in Cartesian terms for x bigger than 0. And of course, it'll come to ground. We'd have to figure out, you know, x doesn't go forever because it's going to drop down below the x-axis. But that's our equation of our motion. You could pop that into a software program like Desmos and see that it's not quite a parabola, but does have quite a parabolic kind of shape with a bit of skew created by the air resistance.